Example 13. Let A be a matrix of order 2. Prove A to the power n, which is A times A times A times A, is equal to another matrix of 2 by 2 for all positive integers n by mathematical induction. Now, I hope you still remember what mathematical induction is. Although in the past, we used mathematical induction to prove an identity most of the time. I think in our curriculum, most of the time identity. But this time, it's not the most accurate to say this is identity, but it's very similar. It's an equation, and this can be called a formula. So the objective is a formula. Other than that, I think everything else is very similar. There is a condition and then the conclusion. Unlike our previous problems, this one looks very short. However, the principle of mathematical induction is unchanged. We will start by saying, oh, the first statement is true. So when n equal 1, the left-hand side, very short left-hand side. This is not the left-hand side. This is the condition. Left-hand side is this. an. So when n equal 1, left-hand side equal a. And that is equal to 3, 0, 1, 1, a matrix. Right? And right-hand side, right-hand side equal, just by substitution, 3 and 3 minus 1 divided by 2, 0, 1. And this is also equal to 3, 0, 1, 1. Therefore, left-hand side equal right-hand side. The first statement is true. Now, usually it's simple to verify the first statement. Now, we have an assumption. Assume that P of k is true for some positive integer k. That is to say that the left-hand side and right-hand side are equal. You have to write it out once. The left-hand side and right-hand side. 3k minus 1 divided by 2, 0, 1, 1. Okay? Now, after this assumption, we will verify the next statement when n equal k plus 1. Now, when n equal k plus 1, the left-hand side is a to the power k plus 1. It's changed. The power is higher now. And that is equal to ak times k. ak times a. And we have an assumption, so I just put this in. ak equal 3k 0, 3k minus 1 divided by 2, 1. Okay, that's the assumption. And after this assumption, I really have to do the multiplication of matrix. So this is my multiplication matrix. So I'll use the first row and the first column to get the first value. That is 3k and 0. And then again, 3k, 0. Oh no, sorry. Lost again. This is the second row. 3k minus 1 divided by 2 and 1. So that is the second row, the first column. And then this one must be the first row, the second column. So the first row, 3k, 0. And the last one is the second row, the second column. So that is second row, 3k minus 1 divided by 2, 1. Okay. And this one, you can simplify it. I know it's not easy, but you can. That's the first value. The second value is 3k plus 1 plus 3. Oh, no, plus 3, minus 3 plus 1. And this one is 1. And this one is 0. And this one is 1. Right? And that is equal to 3k plus 1. And this one is 3k plus 1. minus 1 divided by 2, 0, 1. Okay, so after calculation is equal to the right hand side. And thus, P of k plus 1 is true, and by the principle of mathematical induction, a to the power n is equal to this 2 by 2 matrix. And this statement is true. The statement is true for all positive integers n. Now this is, I think I heard that in the past that some students learned MI in the past and then it was easy, but this time it's a slight variation, a little bit more application of MI. MI is used on proving a formula based on matrices. I hope that you're still okay with it. There's an exercise right away. So you will finish this exercise because that's very similar. And then afterwards, I uploaded another exercise. It's this one. It's called classwork 10.13. I name it classwork 10.13 because these 3 problems are related to example 13. Let me know if you have finished all 4 questions. Is it fine? All 4 questions. That's the quick practice and also the 3 other problems in the Google Classroom. It's a separate file. Girls, it's a separate file. Also today I won't be turning on my cameras as my camera is broken. I hope you can still understand just through the audio. Okay. Perhaps if you haven't finished, maybe you can listen to me first and then finish later. Some of you probably think that Ms. Chen is crazy because I asked you to do 3 or 4 questions that is very similar. I use the same method. Now, but I want to remind you that in this chapter, learning MI is not our focus. I think that if you can do MI once on matrices, you can do it 5 times. You can do it 100 times. That's not the key. The MI has not changed. MI. So we solve so many problems using MI because I want you to understand the multiplication more. I want you to understand what could become the result of multiplication for different matrices. Okay. Now, the class practice, maybe look at the example. The example is a 2 by 2 matrix. And then this position is 0. Only one position is 0. And then after the multiplication, only one place is 0. The same position remains 0. Okay. And there's a place that's 1, and this place is still 1. So the second column has not changed. It's weird that only the first column changed. The second column has not changed. For this quick practice, this position is 0. So the outcome after multiplication, there's a 0 inside it. And also the principal diagonal has not changed. And then only position has changed is from 2 to 2n. There may be something you need to learn, maybe. Because that means m squared equal 1, 0, 1, and this is 4. And m to the power 3 equal 1, 0, and this is 6, like that. So it seems like that if there is a position that's 0, usually it can be observed in the outcome. And if their position that is 1, and usually you can see it in the outcome, not so much, but still, on the diagonal you can see it though, on the diagonal. And then let's look at this practice. Now this one is very similar. This exercise, one moment. This exercise is very similar to our example. In the future, you may hear me call this kind of matrix a triangular matrix because this triangle has value and this is 0. So this is called a triangular matrix. So the triangular matrix after multiplication is still a triangular matrix. The position 0. And next one perhaps I want you to learn the most. It's not because how difficult it is to use MI to prove it. It's actually very simple to prove. It's very simple to prove. If you don't know how to do that, you let me know after today's lesson. But I assume that every single one of you can prove this formula using MI. But you should really learn something. This matrix, I think, is a matrix that only the diagonal principal has value. The other places are 0. This is called a diagonal matrix. Diagonal matrix. Now we say that in the past, in the first lesson, we say, oh, there's a special matrix. Now you should know why. You should know why. You look at the outcome. For diagonal matrix, the outcome is still diagonal matrix. And also for each element, there's a very strong connection, right? What does that mean? After this question, what does that mean? We need to learn that for diagonal matrix, the multiplication, the power of diagonal matrix, it's one step. Okay? In the future, you can use the outcome. You can use it this can be used anytime. Okay, what does that mean? That means for y equal 3, 0, negative 1, 0, that means y squared equal 9, 1, 0, 0 for sure. For sure. And y cubed equal negative 27, 0, 0, negative 1, and so on. So diagonal matrix is very special because the multiplication is very simple for diagonal matrix. The last one. Now the last one is similar. Similar. You see this is also a triangular matrix. The outcome is triangular matrix. So for matrix, the easiest multiplication you can get is from diagonal matrix. Semi-easy multiplication is through for the triangular, that there is a position at 0 basically. There is a position at 0. But still, I don't think for any other than the second last question for this question, in the future you can use it directly. Now for any other matrix of any other kind, I don't think it's wise for us to assume the answer too quickly, because you see, it really follows some pattern. I wouldn't say, oh, there's no pattern. There is a pattern. There's a formula, there's a pattern, but it's difficult to figure out. It's difficult to just imagine it. If you're not given this formula, I don't think it's easy to deduce this formula yourself. But hopefully later on we will have a more systematic way of doing it. But so far, we will say that for most matrix is unknown. It's unknown. Only for diagonal matrix, this multiplication is easy. Any questions? Now you see, matrix is a very strange object. We have to learn from every single question that we do. From this question, we learn a little bit about that, and when we do another question, I will learn something about it. It's not that we need to relearn MI. It's not that. We need to, through every question, through every conclusion, we want to learn something new about it. Okay. Now, if there is no problem, let's move on to the next part. The next part. I uploaded this a few hours ago. Some of you may not have it yet. So this is the last part of lesson 2. The title of lesson 2 is the operation. We've learned addition, subtraction, multiplication including power. The power, a to the power n. And this one is the last one. A lot of students may assume that, oh, the last one must be division. It's not. It's not yet. It's not. Well, we are not going to learn division. We will learn later. It's not division per se. It's some other kind of similar to division. But right now, we will come back to something very simple. This is called a transpose of matrix. You've never heard this before, because in numbers we never have to transpose anything, because it's one value. I don't know how you can transpose it. The only thing I can think of is that if you have 8 and then you transpose it, then will become a symbol that we all love, infinity. So this should explain to you what transpose means. But anyway, for numbers, we do not transpose. We don't do that. But for matrix, we do. You see, there are two matrices, A and B. A transpose is to interchanging the rows and columns. What does that mean? That means the rows in the columns in A is the rows in B. Right? The columns in A is the rows in B. Also, the rows in A is the column in B. So that's the transpose. Okay? We say that B is equal to the transpose of A. That is AT. Transpose A. No, I just say transpose A. I don't say, sometimes I say AT as well. Let's practice. So this 2 by 2 matrix after transpose. So I'll write 6, -3, 2, 4. So that's the outcome. It's another matrix. Now this is the row matrix. After this operation is 2, -5, 7. It's a column matrix. And then this one is a 3 by 2, right? And after transpose, 3, 2, 1, -3, -4, 5. This will be a 2 by 3 matrix. I think for non-square matrix, it's very clear that the transpose of the matrix has a different size. But for square matrix, it's still the same. Is that okay? Now, I know that you have a lot of questions, maybe. Just let me finish first. Because it's something new. Whenever we learn something new, it's all about, oh, why do we learn this? What is the use of this? And then how to use it? And all of questions. But let's not consider those yet. Let's just take the information we have now and look at the properties first. So if we treat this, I know it's very simple. The transpose is an operation. So if we look at the transpose, this operation with the fresh eyes, what conclusion can we get from it? So I think I have 1, 2, 3, 4, 5, 6 conclusions. Some of them are easy, some of them are less easy. It's not too difficult, less easy. The first one, the transpose and transpose, it's equal to itself. I think that's obvious. Right? It's like 8 transpose to infinity and then transpose to 8. It's the same. Right? I hope that's... Now, in the textbook, I don't think the proof is written. I think it's obvious. For the second one is addition, subtraction, transpose is equal to transpose and then addition, subtraction. I would say that the transpose of the sum is equal to the sum of the transpose. Also the difference, but let's talk about the sum. This may not seem very, very obvious, but I think using an example, it should be easy. Should be easy. So suppose A is 1, 2, and B is 3, 4. If we add and then transpose, that is 4 and 6 transpose equal 6, 4. For the right hand side is A transpose plus B transpose. That should be 1, 2 plus 3, 4 and equal to the same answer. I think through this example, you should agree. You should agree. The outcome is the same. Now, after you know this is true, you can use it later. You can. Next is multiplication, scalar multiplication. Lambda is a scalar. Scalar means a number. So lambda times T, so lambda times A transpose is equal to transpose first. That means transpose first and then multiply lambda. I don't know. What do you think? Lambda multiply A transpose. That's the multiply and then transpose. Compared with transpose first and then multiply. Should they be the same? Right? Now here, this can be seen as a proof for 2x2 matrix. I think it's also true for any other matrix. So lambda transpose, lambda A transpose is equal to lambda A transpose. Next one. Next one. Now this one is the most difficult. I think it's the less easy one. Less easy one. That is AB transpose equal to B transpose times A transpose. And that is correct for any matrix. In the textbook, it's listed as one of the theorem, one of the property you prove yourselves. But in today's lesson, we will see a little bit proof when you have to. But the proof, I think that you don't have to worry. Don't have to worry. You try your best to understand. But in the exercise, you don't have to do these similar things. Meaning that later on, you just, as soon as you're able to utilize these properties, and that's enough. You don't really have to prove everything, but during the lesson, we'll prove it. So you feel more confident about the math you learn. Skip that. Let's talk about E and F first. The E and F are very simple because the transpose of I, transpose of I. That is I itself. It's obvious. It's obvious because I is seen as a symmetric matrix, meaning that this is the symmetry line, and then if you transpose it, doesn't change. The last one is 0. 0 transpose is 0. Very simple. Now look at D. Look at D. Why is this true? Why is this true? If you change this, it's not true. Meaning that you cannot swap. You cannot swap the order. It's not true. Yes, last time we'll talk about the order of multiplication cannot be swapped. But this is true. This is true. The transpose of A and B, A times B, is equal to B transpose times A transpose. Let's assume that A is a matrix of, let me see the size. A is the matrix of M times N. I think M times N. Basic is any matrix. Okay, this is M times N. B is a matrix of N times N. Okay, these are the two matrices. Now, the left-hand side, that is A times B and then transpose. So I will assume that this value will end up to be a matrix of size M by M. I hope that's understood. Because a M times N times n times m, the outcome should give you m times m times m. So the outcome is m times m. And every single element inside, I will name it. This is not calculation. I'm just denoting every single one is called Cij. Okay, Ij is just how I call a certain row and certain column. I'm not saying that all of them are Cij. The first one is C11. The second one is C21. Okay, but I call all of them Cij. The numbers inside. And then I do the substitution. I put A inside, B inside. I found that Cij must be calculated from a certain row and a certain column. Because in order to get this value, I must use the jth row times the ith column. Now some students may ask, oh, why isn't it the ith row times the jth column? Remember, there's a transpose, right? After transpose, the jth row will become the jth column. The ith column will become the ith row. So we are calculating the ith row. I must use the ith column. And jth column, I should use the jth row. I hope you know what I mean. It's a mouthful to say. Anyway, Cij will be obtained by using this row and this column. So I write it down. That is Aj times B1I. Aj1 times B1I plus Aj2 times B2I plus basically all of them. That is Ajn times Bn. So that is how I calculate AB and then transpose. Now for the right-hand side, this is the right-hand side. This is right-hand side. Because of the size, now BT, B transpose is M times N. AT is N times N. So the outcome is M times M again. The outcome is it again. So if I put it in, so this is B and T, and this is BT. And this is AT, and this is AT. So in order to get Dij, which is a certain element inside the outcome matrix, I'm supposed to use the ith row times the jth column. So the ith row times the jth column. So that is B1I Aj1 plus B2I Aj2. And then the last one is Bni Aj. Although they're not written in the same order because you can see they swapped. It's not in the same order, but they are the same value. So we know that Cij equal Dij. Therefore, the left-hand side and right-hand side are equal. It looks like I only compared one element. In fact, I compared all the elements. You know what I mean? Because Ij can be anything. So these are two equal matrices. Okay. What does that mean? Later on you will see. Not what does that mean? How to use it. I'll show you example. Example 14. A is a row matrix, B is a column matrix. Find AT, BT, AT. BT. So we swap them. Swap them. And then do this. 1/3 AT minus BT. Of course, you can do the substitution and then calculate. But since we know a little bit more about the transpose now, I think we can do it in a simpler way. Meaning that this is a difference transpose. I can do transpose difference. Transpose and then difference. Okay. And for the first one, it's a scalar multiplication transpose. I can do a scalar multiplication second and then transpose first. It looks like I just took out 1/3, but that is one of the properties we know. Lambda A transpose is equal to lambda A transpose. Okay. And then further simplify, we know that transpose is A. So that is the simplified version. Now I do the substitution because A is just -903 and this one is 1 -2. And then I think it's simple now. You can have another step, which is -3, 0, 1, -1, -2, 4. And then you will get -4, 2, and -2. That's the answer. Last one, A, B, and then T. We can use this formula. Of course, you can skip it, but we can use this formula. That is AT, which we already know AT, times BT, which is. Okay, and then we do the multiplication instead of doing the multiplication first and then do the transpose. You know what I mean? Now we do the multiplication. That's -903 18 0 -6 and -36 0 4. Is that okay? It's a similar exercise. I think the similar exercise. Let me know when you're done. Okay. Now, if you haven't finished, then please try your best later. Don't give up. Now, for this exercise, of course, you can do this transpose. Now, the real something that we call algebra happens here. Happens here. So that is 3m t minus nt. It becomes 3mt minus nt. This is what we call algebra. Algebra means that you can use letters to calculate. You don't have to use the object. You don't have to use the numbers to calculate. Now the rest, if you put it in, these numbers you put it in, these are arithmetics. These are numbers. In this case, matrices, but these are not algebra. This is algebra. And every time when you use a letter to represent a matrix and to do simplification or to do anything, you need to pay attention. You are learning something new. Okay, so that is first example. Second example. Second, do I give you the answer? Oh yes, I gave you the answer. Second example. In this example, let's read it. It's quite abstract. A square matrix M is said to be a symmetric matrix if the transpose is equal to itself. Now this shouldn't be too hard because just now I mentioned that I is a symmetric matrix because I transpose equal to I itself, right? Also other things as well like this. 1, 2, 2, 1. Transpose equal 1, 2, 2, 1, right? This is also symmetric. So something about this idea, a symmetrical matrix. Now if P and Q are two square matrices of order 3, and I be the identity matrix of order 3, and mu to be a scalar, let's see the conclusion. The conclusion, the first thing you need to show is that condition Q is symmetric. Show that conclusion, this is also symmetric. I think in this question you can taste that it's all algebra. It's all algebra. Let's prove it. Condition Q is symmetric. That means QT equal Q. This is given. Symmetric, then QT equal Q. Now, how about the objective? The objective is quite complicated. It has two parts. Let's simplify it and see if it's still a symmetric matrix. So I will take this objective and then look for its transpose. So PQPT plus mu IT is equal to, you can see I'm using the properties one by one. So I will split them. The first thing is to split. The second thing, I think we should work on this first. For this one, I will take out mu and then this will be I. Again, I'm using the property. The scalar multiplication can be done later. Now, how about the first one? The first one has 3 matrices and then transpose. But what do? I will make it one matrix times another matrix. It's just the other matrix is bigger. So in this case, it's P times QPT transpose it should be equal QPTT times PT. That's what I'm going to put it in. Because ABT equal BTAT. And here's what I do. This is QPTT times PT. Okay. Now, for this one, I can further expand, right? So for this one, that is PTT, and this one is QT, and this one is P. And then for IT is I. And then for this one, PTT is P. PTT is P. QTT is Q. And PT is PT. And then plus mu I. And then after, I think, 3 or 4 steps, it's either 3 or 4, up to you. After a few steps, you will say, you will find out that this very complicated matrix is indeed a symmetric matrix. Okay. So that is pure algebra. Pure algebra. We don't know what PQ are. We don't know. Am I right? I think I'm right. No. I think I'm wrong. I put a more like a one single T. I shouldn't put it's PTT and QT, not QTT. It's QT. I think there is a mistake here. It's QT. I wonder why. But it doesn't matter because QT is still equal Q. So it's so true. Anyway, I don't know what P and Q are. I do know what I is. I is identity matrix. But I don't know what P and Q are. But anyway, no matter what they are, as long as Q is symmetric, the outcome is symmetric. Now, I think part B is a little bit simpler because now R is given. Since R is given. Now see, R is given, and R is symmetric itself. You can see. You can see. Anyway, so this objective, is it symmetric? I think that you can try thinking about using the result of A because it's very similar. So first I need to find out R squared. Now R squared, I'm not going to find a shortcut or anything. I'm just going to find R squared. This is a real multiplication, so I'm going to do it very quickly. So this is -1 times -1, 2 times 2, and the last one is 0, so I don't write it. So 2 times -1, and then 2 times 0. The last one is 2 times 2. And for this one, it's 2, 0. And for this one is 2 times 2. 2 times 0 and 2 times 2. The last one is 0, 0, 0, 0, 0, 0, 0. It's all 0. This one is -1 times 0, 2 times 2. The last one is 0, so I don't write it. This one is 0, 0, 0. And the last one is 2 times 2. So the outcome is 5, And this one is -2. This one is 4. I suppose the side is the same. -2. 4. This one is 8. This one is 4. And it's 0, 0. Okay. So I'm not finding any shortcut. I'm saying, oh, this is R square. And R square is symmetric. I hope you know. Although these numbers are not equal, but that's fine. As long as the transpose equals. So R square transpose is 5, -2, 4. -2, 4, -8, 4, 0, 0. It's equal to itself. So R square is symmetric. R square is symmetric. According to part A's answer, if we let Q be R square and mu be 3, mu be 3, comma, and then this is a symmetric matrix from the result of A. Okay. Now, in this question, there is an alternative method because that we know R itself is symmetric. The first step, I can prove that R itself is symmetric. RT equals itself. So R is symmetric. Now, since R is symmetric, let me ignore this. R squared transpose is equal to R transpose. That is equal to R transpose times R transpose. That is equal to RT squared. Huh? What am I trying to? RT trans, yeah, yes, this is correct. And then that is equal to R squared. Because RT equal R, right? It's RT equal R. So here, let me do it. R squared T, it's RRT equal RT times RT. That is RT squared. And RT equal R. So I proved that R squared is R squared T equal R squared. Therefore, R squared is also symmetric. Now, this method, I think I will not have to do the multiplication, not really carrying out the steps of multiplication. I can conceptually think that, oh, if R is symmetric, R squared should be symmetric as well. Okay, now since R squared is symmetric, and using the result of A, I will know that, again, this is a comma. If Q equal R squared and mu equals 3, this outcome is a symmetric matrix. There's an exercise. Please have a look. Finish when you're, let me know when you finish. Okay, I see that most of you have finished. This is the answer. Part A is pure algebra. I hope you enjoy this though. I hope you enjoy this as much as you enjoyed algebra in S2. Because you've practiced the arithmetics for 5 or 6 years in primary school. You always add, subtract, but then in S1 and S2 you learn to use letters. And this is to use letters. And the conclusion is, I think, quite simple to obtain if you understand the properties well. And the second part here, in this case, if you want to use the result of A, that means P is equal to R squared in this case. Is that okay? Now, in the example, I have an alternative method. The question is, does the alternative method in the example still work for this question, this quick practice? Does it work? And why? Now, who can answer that? The internet connection may not be very well, but I'm trying to ask one of the students. Can I ask Sophia Cheng? Hello, Sophia.
Miss Chen, can you hear me?
Yes, I can hear you now. I cannot hear you.
I am still thinking.
Now think about the second method in the example. Because R is symmetric, therefore R squared is symmetric. I consider this method is simpler because I don't have to find R squared. Because the original method, I have to find R squared and say, oh, it's symmetric. But without finding R squared, I can say it's symmetric. So that is the alternative method. Think about whether or not this method can be used in this class practice.
No, because R is not symmetric.
Correct. Correct. This is quite funny. You see that R itself is not symmetric. But R is symmetric. Sorry, R squared is symmetric. In the example, I think it's more obvious because R itself is symmetric. So R squared must be symmetric. But this one, R itself is not symmetric, but R squared is symmetric. This may be very difficult to understand. So that's something new we learned about. This method does not work. The second method does not work. But that is not the main thing that we learn. We learn something more about matrix again, is that if A is symmetric, A squared is symmetric for sure. If you say it in this order, the conclusion is in this order. A is symmetric, A squared is symmetric. But if A is symmetric, or you may think, oh, does that mean A is symmetric? No, not necessarily. So you should know that just because A squared is symmetric doesn't mean A is symmetric. A is not necessarily symmetric. For this example, you can learn even more, is that R square does not have any zero in it. Oh, sorry, R square. R does not have any zero in it. But yet R square has 2 zeros. R square is diagonal. Isn't it? I guess that to understand this feature about a matrix, you may use something like, you see, 6 is not a multiple of 9, right? As a comparison. 6 is not, but 6 squared is. In other words, just because 6 squared is a multiple of 9 doesn't mean 6 is a multiple of 9. You know what I mean? Huh? Right? But you know that 9, anything that has, for example, 90 is a multiple of 9. And then you can just rest assured that 90 squared is a multiple of 9. So if you change this to 90, and then obviously 90 squared is a multiple of 9. So you can say it backwards. You know? So the symmetric matrix is not like, it's not so easy to understand. Something not symmetric can get you symmetric. This happens all the time in math, but you maybe in the past you didn't pay much attention. Some similar things can be, now on top of my head, I would think that this a multiple thing, it's very similar. And something like I is not a real number, but I square is a real number. Something like that. Can we say that? I is imaginary, right? I is not real, but I square is real. Something that's not symmetric, but after square can be symmetric. Something that's not real, but after square, it can be real. Just things like that. Things that. Also, it reveals something very special about matrix. You can learn more, like, oh, what could get me a symmetric matrix? What do they look like? It may look like something weird, but this after square may get you not just symmetric, but diagonal as well. So that is it. Now, before we end the lesson, I want to talk about the purpose of learning this very strange operation, the last one. The meaning in math is not very significant, I must say, the transpose. Like you have this and then you take a transpose. That's very easy to be done. It's very easy to be done. The properties, all of them seem very obvious other than D. This one looks like something mysterious, but after proving, it's okay. It's okay. The meaning of the transpose, this operation, I think you can take reciprocal, for example. Now, in the past, when we learn about numbers, we learn, oh, this is 1/5. And then it has a reciprocal that's 5. That's an operation. You know what I mean? The process of finding a reciprocal of a number is an operation. Now, is it very essential? Find the reciprocal. Is it very essential? The operation itself is very simple, very straightforward. It's not essential. Without reciprocal, you can still do all things, all sorts of things. But with reciprocal, sometimes you find, oh, this is easier. It's just more convenient. Okay, that this operation cannot be put as a similar status with addition, subtraction, multiplication, or even scalar multiplication. It doesn't have a very significant meaning behind it. It's simply because we need to use it all the time. So we give it, we need to learn about it, to further learn about it as well. Now, what does it do with the, it mixed with the addition, subtraction? What does it do with the multiplication? And what if I do it twice? What if I do it to a special matrix? And these things we need to know. But it doesn't change the whole picture. It doesn't change the anything very essential about matrix. It's not the same as addition, subtraction. What I mean is that okay? So that is, I think, the second part of the lesson. Now we don't have much time, so I will end the lesson today. Last time I assigned homework, but I didn't have time to mark yet. I will mark in the next 2 days, and then you will do another round of homework. Hopefully every time when you solve a problem, you don't just say, oh, I finished this. You need to think about, what does it tell you about matrix? Because matrix is new. There's nothing to do with it. It's completely new. Anything oh, this may be interesting, and this may be interesting. You need to accumulate those knowledge, and later on you may need to use them. I'm serious. You may need to use the result that you learned from your homework. Yeah, just like this one. This one. The classwork, remember? The classwork. This one. Just as this one, this result in this exercise, it's not even in the textbook as a theorem or as a property, but I'm very sure that later on you will use it. You will use, oh, this to the power n is this. And also today, I am pretty sure that you need to learn later on, you need to use this result quite often. That is QQT, not QQT minus P, because that's quite difficult. But for any matrix, any matrix, QQT is symmetric. Think about it. For any matrix, QQT is symmetric. Isn't it? So if you want to create a matrix, a symmetric matrix, you can also, oh, QQT must be something like that. So you need to accumulate this knowledge. This will help. This will help you solve a very difficult question about matrices. That's all for today. That's all for today. If you have any question, let me know. Otherwise, you can go.